designing power electronic converters for any of the system, then this is very, very important, right? So now let us see why this modeling of power electronic converter is required. So we know that this is our, let's say, DC to DC converter. Okay, and any converter, this is our V input, this is load, this is output. Happening if I need, let's say, let me go to okay, so it becomes 11 volt. Now please check now if it is fine. Is it fine now? Okay.
Not so much, sir.
अभी मैंने ईयरफोन हटा दिया है, right? Okay, so if this is duty cycle is 0.5 and input has become 22 volt, then output will be 11 volt. But I do not want 11 volt. I want to regulate output to be 10 volt. Now in this case, this is not good that we are getting 11 volt instead of 10 volt. Then what we do? We do it feedback, right? We do it feedback, and based upon the feedback, we compare it with the reference. That part I will tell in detail in control system design. There will be error. Now this error will be processed in a controller. This error will be processed in a controller, and accordingly this duty cycle will be manipulated and set such that even if there is 22 volt input, I should get 10 volt output. So that is our aim. But in order to design this proper controller, what we have to have, we should have this physical system. So I will design, let's say, PI controller I'm designing for this. So what will happen? Every time I have this physical system, and every time I need to provide 22 volt, then tune the parameters, then 18 volt, then tune the parameters. So if I'm doing that way, then it will be very difficult. Understand in another way. For example, let's say I need to get haircut. Okay, and for that purpose, what I do, I have chosen specific hairstyle, let's say. Then I go to the barber shop, I show him, okay, I need this proper haircut. Then what he will do? He will try to cut my hairs in that fashion which I want. But that is, not proper. Or let's say in another way, he has certain 100 styles, and I say, okay, I want this particular haircut. Okay, then he will try to cut in that way, but quite possible that he is not able to cut exactly the same things which I wanted. Now what I need to do? I need to wait for 2-3 months. I have to grow my hair again, and then again I go to him. Then what he will do? He will again try, and then will again try. This is second time, third time, and fourth time. So in this way, he comes to the perfection. Let's say 1 year went away. Okay, and I wanted to get this haircut to attend some marriage function. Now marriage is already over when that was to happen next day only, right? So that is not the proper way. But instead of that, what could be done? He has, let's say, 100 styles in his computer or some software. Then he will take my pick, and he will put my pick over there, and he will show, okay, sir, this hairstyle is like this is like this is like this. Which one is suit to your face? That you please tell me, that I will cut. That way it become easier, right? It means, what is the picture? Picture, I'm the physical person and picture is just my modeling. The picture is representing my features. So as much as accurate is picture, then whatever desired things I need, that will be happening according to me, right? Now the issue is that if that picture is not proper, in picture, let's say my facial expressions are not captured properly, if in pictures my nose is not properly, my eyes, something is not captured properly, then what will happen? I'm different and picture is different. So whatever you assume those 100 styles to be controller, so those controllers will be working on the picture, not on actual me. So whatever results I will get, it will be dependent upon that picture. So if picture is accurate, then results will be accurate only. Similarly here, if anyhow, because every time I cannot put the real physical system in the field and design the controller, because maybe some power plant is there or some other system is there that is already working, but you just want to improve its performance. That's why you would want to design a compensator controller, right? Now you cannot, you cannot do your permutation combinations of controller design in the actual running system, because it may get damaged. But what is the alternative then? Alternative is that if I can capture the dynamics of that real plant or physical system in some mathematical form, then that mathematical form is called mathematical model. And now this model, if it replicates the physical system as accurate as possible, then what will happen? I can play with these mathematical equations, I can play with these mathematical models, and I can design thousands or hundreds of controller for that. And whichever controller works fine with these dynamics, that I will say, okay, I will go with this. Then what I will do, I will make a small prototype of that system and will try to implement this design controller over that. If it is giving me satisfactory result, then I can dare to implement the same thing on the actual plant, right? That's how it works. So we cannot directly take the physical system into our research and do the things. But if we can capture the mathematical, we can capture its dynamics, transients, steady state, everything we can capture, then it will be really nice, really easy for a control engineer to design the controller. So mathematical modeling is part of that only. In mathematical modeling of converters, if I talk about, we try to capture the dynamic converter. Second is SSA, popularly known as SSA, state space averaging. The second is averaged switch model technique or approach. And the third one is, there are various switching flow graph, or this yesterday's I told bond graph. You can say bond graph technique that is based upon kind of switching flow graph techniques, bond graph. And energy factor approach is also there. Energy factor approach. Others are current injected equivalent circuit approach, transformer circuit approach. So many are there. So these two are very important. And even first one is popularly used due to its simplicity. So we'll talk more about this state space averaging technique in detail. So Let's go to averaging technique steps one by one. So step one is that it has few steps. So we will go step by step. So step one is that we will take first generalized state space averaging technique, generalized. Then we will specific example of buck converter and how to use this, that we will explain. So formulation. So in formulation, you know, a buck converter or any different. Okay, right. Let me see. Is वेरिएबल आप किसमें चेक करना सही आ रहा है कि नहीं आ रहा है? हाँ? सही आ रहा है वेरिएबल systems audible, is it audible? Variable structure system. So what does that mean? Variable structure system is this system is varying depending upon the position of switches, right? So this is called variable structure system. If switch is in this position, switch is on, diode is off, then we have one circuit. If diode is on, switch is off, then we have another circuit. Voice is not clear. नेट तो लेन से चल रहा है हमारा तो. हाँ? Voice is breaking. Just a minute. Let me resolve this issue. Voice is breaking. You can turn off the camera. The voice will be clear. I think camera is already off now. Camera is already off. Maybe sometime it's due to internet connection. Okay. Okay. So we were here. I'm writing most of the things. That's why if you are able to see screen, please. If sometime it is not audible properly, you can read on the screen also. Okay, so what is happening that when switch is on, it is having one circuit. When switch is off, it is having another circuit. That's why it is called variable structure systems. So if we talk about CCM, and we have in CCM there is two modes. So far DCM types we get, and then there are three. If it is DCM, elements. These states are decided, right? So here, if one inductor, one capacitor, two states, or order also second order. Two inductor, two capacitor, like a converter, fourth order state will be four. If three inductor, three capacitor, states will be six, sixth order. So depending upon that, the order will be defined, right? Now let's assume that we are having converter in CCM and let's say n modes, then converter will be of, right? I'm separating in lay mode 1, mode 2, mode 3, mode 4, like that, right? So this time interval and time interval should be equal to t. T is divided into n parts. So for, let's say it's at 100 microseconds. So maybe for 6 microsecond, one mode is there, 20 microsecond, other mode is there, 50 microsecond, like that it will be there. So total should be 100 microsecond. But if it is having 2 microsecond, let's say, sorry, 2 modes only, then if it is 100 microseconds, so let's say duty cycle is 0.6. So for 60 microsecond, it will be on. For 40 microsecond, it will be off. Like that, 2 modes are there, we consider it. So one mode will be when switch is on, another will be when switch is off. Let's say if it is DCM, then there could be 3 modes. One is when switch is on, second is when switch is off, but inductor current is not 0, and third will be switch off, but inductor current is 0. So like that, we, let's say, we have identified the number of circuit state operation. Here we write each state of circuit operation. So we will write equations. Yeah. So we will write equations. Now, what is the states we are taking? States, we take capacitor voltage and inductor current. They are chosen as states. Okay. So now we define, we take input. What is the U input variable? That is V input normally we take, right? And control variable we take D. So in that way, let's say we write the when switch is on for, let's say, D into T period, then we write these equations and we formulate them. X dot T equal to A1 xt plus B1 ut, Y of t is equal to C1x plus D is used for duty cycle. That's why I normally use E here instead of D. Standard way is AX plus BU, CX plus DU, but I'm using E here. 1 denotes the mode 1 where switch is on. Similarly, when switch is off or mode 2 is there for 1 minus D into T period, I can again write these state specifications. So that is X2 plus B2 UT, YT is equal to C2 XT plus B2 UT, right? So these equations we have written. Step 1 is complete. Now step 2. And step 2, as the name suggests, state space averaging technique. We have done state space model in individual mode. So one is when switch is on, one when switch is off. But we need to get the unified model of the circuit. So one circuit is operating for DT period, another circuit is operating for 1 minus DT period. So in order to get the unified model, what I need to do? We need to do averaging over one switching cycle. So the second becomes finding the average state space model. Finding the state space model, average state space model. How that is done? This model is for D into T period. This model is for 1 minus D into T period. So we just multiply these equations with D into T, multiply these equations with 1 minus D into T, add them, divide them by T. So we get the average state space model. So what is that? In this case, if you multiply this, then this becomes d upon dt x bar of t equal to a dash. So I'm writing one. Let's say we are multiplying this with a1x dt plus a2x 1 minus dt, right, divided by t. So what is happening? What we are getting, a1d plus a2 1 minus d into x, and t will cancel out. So the first term which we will get, let's say I represent it to be a dash. So this is a dash, right? xt plus b dash u average t. Similarly, this y average t, that will be c dash xt plus e dash ut. Where likewise this terminology we have represented with a dash. Similarly, b dash will be b1d plus b21 minus d. C dash will be c1d plus c2 1 minus d, and e dash will be e1d plus e2 1 minus d. Okay, so we have got this averaging. Step 2 we have complete. Now this bar symbol represents just averaging of the equation. And how does it actually works also? So let's say this is the your dynamics of converter, right? So what we are doing, it's varying with the time, and this time period depends upon switching cycle, which is, let's say, if it's a 1 kilohertz, then it's 1 millisecond, 1000 microsecond. If this is switching frequency is 1 kilohertz, then this is 1 millisecond or 1000 microsecond. So if switching frequency is 10 kilohertz, then this will be 10 microsecond. Okay, so we take 10 microsecond part from here, right? In which also some part is on time, some part is off time. So what we do, we take averaging over that, right? So this is very small time. We are doing averaging over that. Now, step 2 is complete, but what is happening here? This A, which a1d plus a2 1 minus d, right? Now d is also varying with the time. This is not constant, right? This is also varying with the time. Slight variation will be there, because we know that output voltage is not always the constant. It is having some ripple, due to which this d will also slightly varying. Now this is function of time, and this xt is what basically? This is xt is basically your a vector which is having capacitor voltage and inductor currents. They are also function of time. So this is function of time. This is xt is also function time. A dash is also function of time. So this equation is non-linear. There are two input together, right? If both varies, then this output will also vary. It will not be working in linear fashion. Now, this model is not linearized. This is state space average. This is averaged, but not linear. So this is non space averaged, state space averaged non-linear model. Now in the next step, what we do in next step, we will do linearization. Step 3. Linearization. Linearization by introducing small AC perturbation around a DC operating point. Okay, linearization. So what is this? First, let us do why we are doing linearization. So let us say this is some system dynamics, right? It is varying in this way. But most of the time, I think that my system will be working around this value. You know that, let's say if I say my converter output should be 10 volt in general. So, but sometime I may need 8, sometime I may need 12. But I cannot say that I have designed some converter for 10 volt and sometime I need 100 volt from this. Never, right? So similarly, input voltage, let's say nominal, I say 20 volt I have designed for. But okay, it may vary 18 volt, it may vary 22 volt. But you cannot say, okay, I have designed for 20 volt input nominal, but if input volt varies to 100 volt, that way we cannot design any system, right? Any practical system. whatever, like our instruments also, they have certain variation in input. But if suddenly in home you have rated up to 230 volt, or maybe some plus minus 20%, 10%, but suddenly if you feed 440 volt to that equipment, definitely that will not work. That will work. Similarly here also, mostly we know that our converter will be operating around this DC value. So, but some variation may be allowed. Some variation may be allowed. So that's what we can consider this particular portion to be linear, and that's why we call it to be linearization. But if I draw a line around this perturbation, then I say, okay, some points are nearby, so there is not much difference. There is not much error. But if I take these points, they have large error. Why? Because they are far away from this DC operating point. And that's the reason whatever controller we design based upon these linear models, whether it's a transfer function or maybe linear state space model, that will work when there is small change in the circuit. They will not take care of the large fluctuations. The only reason is that when these controllers were designed, it was assumed that these models are linearized around DC operating point. So they will behave around DC operating point. But if more fluctuations are there, then we have to go for non-linear techniques, which may be used or which may cover this entire range, right? Which may cover this entire range, not only this nominal point, right? So obviously for everything we need to pay. If we need to take all functions in one mobile, then you have to pay more, right? And if you know, okay, I'm a student, I just need to call and SMS and sometimes WhatsApp, not gaming and all, then you can go for lower version also. Lower processor will work. But if you all in one, so you have to pay everything. Then your cost increases, size increase, all issues is there, right? Okay, so we consider that our demand or the user's need is that system should work around the DC operating point. So the next step, as I said, linearization. So linearization means this is our actual variable. Now it is varying around a DC value, right? It is varying around a DC value. So this is DC value and this is the variation around this. This is variation, or you can say perturbation. So this tilde, when we represent with tilde, X, capital X is the your DC value, fixed value, nominal value, and X tilde, or sometimes it is also denoted by X cap. That is called perturbation or small change. Okay. So this is like this. So similarly, we do it for all variable. Y of t is y plus y tilde t. U of t is equal to u plus u of t, right? Similarly, d of t is equal to, oh, sorry, not this will not be there. D plus d of t. What else is left? Like that. Okay, so we go back to our equations. So what was our equations? D upon dt x. So we represent it with x of t equal to a dash. A dash was there. So what was a plus d plus a dash plus a2 1 minus d. So 1 minus d means 1 minus d cap, right? So let me this one only. This we can pick it. I think there is option for this. Select option. Scroll. Yeah. So we can, I think, capture this portion. No. C. Control. Yeah. So these are our equations. Okay. Just for reference, I put it here. Okay. So dy dt x I represented with this a dash, and a dash for yeah, a dash is a1, so I wrote a1. D is d plus dk plus a2 1 minus d, right? So this is a1 is complete. X, so this is x plus x cap. I'm just not writing this t now. You just consider x tilde or time value only. Okay, just for simplification of the terms. Then plus b1 d plus d cap plus b2 1 minus d cap u plus u. Okay, so let me first simplify this, then we will go to this y term. Okay, so x is the constant term. So d x upon dt, constant term derivative is 0. So this is 0 plus this is d upon dt x. I can t. First, if I can say d2 1 minus this is happening between internet connection only. 0 plus x dot equal to, now this term I'm writing, this entire term, sorry, this a1d plus a2 1 minus d, I'm writing it capital A. Okay, remember the difference between a days and a days were a1 small d plus a2 1 minus d, where small d were having perturbation as well as dc value, but here it is capital A is capital D, so it's a fixed value. DC capital D is a fixed value. So A1 plus A1 minus A2 D x plus x tilde plus B plus B1 minus B2 D tilde U plus U tilde. So far we have not done any approximation, right? Still these terms are non-linear only, right? We have not done any linearization. Now equal to, let us simplify this. So this is ax plus a1 minus a2 x d cap plus ax cap plus a1 minus a2 d cap x cap. Okay, where d and x are function of time. So this is our first term plus bu plus b1 minus b2 u d cap plus bu cap plus b1 minus b2 d cap u cap. Okay, now we are introducing linearization. We are edit linearization. Say here these x values were very large than these. This is also time variable. It considers to be set. Ignore because the time variable. We ignore the higher order terms. We ignore or neglect. We neglect the higher order terms. If we neglect, so I'm just removing this part. No, this is not much required. Okay, so neglecting the higher order terms, what will we get in term? 0 plus x dot. Now this term is neglected. Similarly, this term is neglected. So what is left? Only remaining equations. So I just collect these things: ax plus bu. So this term is collected. This term is collected. Now next I'm collecting this term plus a1 xk. This term plus b u cap. Okay. Now remaining is this one a minus a2x so plus a1 minus a2x. Okay. Plus d I will take out b1 minus b2u and d I am taking out. So this is my first equation, state equation only. Similar way I can do for this also. I can simplify this second equation. So what I will get here in this y plus, because here this is not y dot, this is y only. So I will replace it with y of t. Okay. Now after this equation is y equal to cx plus u. So this becomes cx plus eu plus cx cap plus eu cap plus c1 minus c2x plus e1 minus e2u d cap. Okay, so this is called large signal linearized. Average. Linearized. The next step 4. And, these equations I just rewrite here. This is 0 plus x of t will equal to ax plus bu plus ax plus bu plus bd d cap. What is d cap? I will tell. And then I can write y plus yt cx plus eu plus cx cap plus eu plus ed into d, where a is a1 minus, sorry, a is not this, where a is a1d plus a21 minus d, b is b1d plus b21 minus d, c is c1d plus c21 minus d, e is e1d plus e2 1 minus t. Now there is new terms bd and ed. Why I took those terms? Just let me tell you previous slide. So these a1 minus a2 they are constant. X is constant plus b1 minus b2 that is also constant. U is constant. So this is a constant matrix. Similarly, c1 minus c2x plus e1 minus e2u that is also constant. So if I can represent this with a single term bd and same thing here this with single term ed. So that's what I wrote. So here bd is a1 minus a2x plus b1 minus b2 u. Similarly, ED is E1 C1 minus C1 minus C2 x plus E1 minus E2 u. We got these equations. These equations are in state space form, right? They are in state space form. And you can see this is the DC part and this is DC part over here. This is perturbation terms and these are perturbation terms. So in step 4, what we do, we separate steady state model first. So for steady state model, obtaining steady state model, what we do, we compare it. So zero is not simple zero here. Zero is kind of a vector, right? Zero is kind of vector which is same dimension as x. So this is zero vector. Zero is equal to ax plus bu, and this y is equal to cx plus eu. This is called our steady state model. And from this model, we can get the steady state value of various variables. So let us solve this. If I solve this, so this is minus, you can say ax equal to minus bu. From here, x is equal to, if I pre-multiply A inverse both sides, then this becomes A inverse into A becomes unit matrix. If I multiply that with I, with x, then it is x only. So minus A inverse bu. So this x gives me the value of this steady state value of the state space variables, which is our inductor current and capacitor current. If I put it back over here, then this y is equal to C minus A inverse bu plus u. So let us take u to be common. So this becomes minus C inverse b plus u. The output voltage equation. So these two equations are very important for getting directly. If we know A, B, U, directly we can get the DC values. No need to do other analysis. Now this is called steady state model. So second is, which is also very important for controller design point of view, that is called small. This is steady state model or also called DC model. Now next one is small signal model. Small signal model, or you can say transient model, or sometimes it is also called AC model. So that can be obtained. If we equate these terms, right? So this x of t, that is equal to ax plus bu plus bdd to of u plus e of u plus ed equal to small signal model space. This small signal space. So if you know any techniques, you which are based on, then we can use six steps. If we do, we determine the transfer functions. We determine the transfer functions, various transfer functions. So while determining transfer functions, what we need to do, we just the Laplace transform of this. And because you know the basic definition of transfer function is that it is the ratio of Laplace transform of output to Laplace transform of input with initial conditions 0. That is very important for transfer functions, and that is the reason we go for modern control, that this transfer function does not take care of the initial conditions. That's why state space model takes care of that. Already, that's the beauty of this modern control system. But okay, if linear controller is giving us the better result, we can go for that. Okay, so how to get the transfer functions from this? So initial condition is 0, and we put it over there, and let's take Laplace transform of these models of state space model of obviously linearized model. If you take Laplace transform of this is x dot t. It's a differentiator, so x of s, okay, equal to a x of s plus b u of s. A, B, B, D, all these are constants, so they will not having any impact due to this Laplace transform. So another is y of s is equal to c x of s plus e u of s plus ed d of s. So these two equations we are getting from Laplace. Let's simplify it. So first one, if I simplify, so this is s. If I'm taking this to be here, then this is s minus a x of s equal to b u of s plus bd d of s. Again, I simplify it by pre-multiplying si minus a inverse both sides. So x of s still, that is equal to si minus a inverse b u of s plus si minus a inverse bd d of s. Okay, so this is what? This is our x of s. This is also very important. Okay, now we put it here. So from this we get y of s equal to c s minus a inverse b u of s plus c s minus a inverse b d of s. This term is over, plus e u of s plus ed d of s. Now u of s is common in both two, so we take it together. So c si minus a inverse b plus e u of s plus this term only c si minus a inverse bd plus ed d of s. So this is the second Laplace transform equation which we get. Okay, so we can also box it. This is also very important. Okay, so this is also boxed. Now this equation is also important. How to interpret this and what is this meaning and how many meaning? One is inductive input voltage. Sometimes you may take this out and also the variation. So from here, if I want to get, so U is your VG and D is there, and X is representing IL and BC, right? So if you want to see the variation, the effect of this variable U on X of S, then how will you write X of S as U of S? Then you will get Si minus A inverse B. Similarly, if you want X of S with respect to variation in D of S, then you will get Si minus A inverse BD, right? So from this, how many transfer function you can get? IL upon VG or V input. One other you can get V output or capacitor voltage upon input voltage. These two you may get. From this, how many you can get? You can get V output, not V output, IL with respect to duty cycle and VCS with respect to duty cycle. So 4 transfer function you may get from here. Similarly, if you take these equations, this equation, so what you can get Y of S with respect to U of S, that is nothing but C Si minus A inverse, Si minus A inverse B plus E, right? So from here you can get 2 transfer function, Y V output, two transfer function. One is V output with respect to BG. Another equation will be your Y output with respect to duty cycle. So that will be given as C Si minus A inverse BD plus ED, right? So from here you will be that we can see, we know, we know, ED know, everything we know. So directly just using these equations also we can get the various transfer functions. Now it's not always necessary that you need to obtain all transfer functions. So what is this transfer function is telling? IL of S upon VG of S. This transfer function is telling that how the variation in the input voltage, that is disturbance, kind of line disturbance, affects the inductor current. How the disturbance in input voltage affect the VC of S, capacitor voltage. How the disturbance in duty cycle affects this inductor current, affects this voltage. Similarly, how the effect in duty cycle affects the output voltage, how the changes or variation in input voltage. Okay, how these changes in, I will not use yellow color now onwards. I think it's not properly visible. Okay, so how the variation in input voltage affects the output voltage. So these transfer functions are basically denoting that. But which transfer function is more important from controller point of view? So if you are using, when you will see that if you are using single loop control, where directly you will control the output voltage. Yesterday sir was telling constant voltage charging. In that case, we will be using this V naught of S upon D of S. How duty cycle is affecting the output voltage, because we will get this error. We will get this error output. But if you are अभी 10 मिनट बाद अभी सर ने भेजा होगा ना उनको 10:30 मिनट हो so if you are using current control approach है ना, then you need to fix the current. In that case you need this transfer function IL of S upon D of S. So it shows that how variation in duty cycle will affect the inductor current. So if you are using current control, then you need this transfer function. And if you are using only voltage control, then you need this transfer function. And if you are using multi-loop, which we will discuss in control system, then we need both the transfer function. So it depends upon that what is our requirement. kind of control we are designing, then we accordingly use the formula. So these are the detailed explanation which I have told you. Now you can directly obtain the state space equation in mode 1, mode 2. You will get A2, B, B2, C, C2. You know the duty cycle value. With the help of that, you can get ABC, right? Now, if you once get ABC, then we can get this value X minus A inverse BU. You can get Y value also. So the XY also we got. Once we got the X value, then we can get VD A1 minus A2X plus V1 minus V2U ED C1 minus C2X. So got BD and ED. So all these 6 matrices are required for getting this 5th and 6th matrices or vectors. We need value of X, which is given to us 10 minutes. Okay, so that we can get. Now once we get it, we can directly use formula. Let's say we want this V node upon D, so that is nothing but C Si minus A inverse BD plus ED. Now everything is with us. We just need to multiply the matrices and add them. We will get the transfer function. Now that is okay. One term here, multiplication is easy, but you know that finding the inverse is a bit difficult. Finding the inverse is a bit difficult. And matrix, if it is the, let's say, ideal buck converter, then this is 2 by 2 matrix where maybe some components are 0 also. But if it is the fifth order matrix, it is the 5th order matrix, 6th order matrix, 6th order system, then this matrix size is keep on increasing. And what is the basic formula for inverse of any matrix? Let's say matrix is there. What is the basic for, let's say, Si minus A is our matrix. So if you want to get invert of this, so what is the basic formula? Adjoint of Si minus A divided by the determinant of it, right? So you know, adjoint, getting adjoint for a second order matrix is easy, but for getting a 4th order, 5th order, this adjoint becomes difficult to get. First thing. Second thing, if you further get involve the non-idealities in this system, then this becomes further more complex to get the inverse of this, because everything you need to do manually. The reason being is that this S is coming into picture. S is a complex variable, so it is difficult to solve it. Using these digital computers as well. And S is the there is ways in MATLAB nowadays, but still it needs good command on coding, and then also you will not be getting the transfer function in one go very easily, right? So that is there. So due to these limitations, if higher order converters or maybe non-ideal converters are there, getting this is called Si minus A inverse is called resolvent matrix. Si minus A inverse Si minus A inverse. This Si minus A inverse. It is called resolvent matrix. Resolvent matrix. So there are algorithm. One algorithm is there that which is called generalized, which is called Leverel algorithm. So this Leverel algorithm makes it very easy to find out the Si minus A inverse of a system, irrespective of its complexity, makes easy. Okay. So the issue is that if you go with this formula, then if you want to get the generalized transfer function, then sometimes it becomes difficult to check whether the whatever inverse you have obtained that is correct or not, right? So we will learn this Leverel algorithm. We will learn this Leverel algorithm. So what is that Leverel algorithm? We will learn. We have 2-3 minutes break, or maybe 5 minutes break in between. We'll start our next topic and the implementation of whatever we learned to obtain the model of a converter. Okay, so we take 2-3 minutes gap, then we'll be back. Okay. So, is it audible to you and screen visible? Please let me know.
Yes, it is visible.
It's visible. Okay. So, okay, fine. Thank you. So, what we have discussed that there is issue with getting this Si minus A inverse if the size increases, right? Now, how to resolve that? So, for that, there is one algorithm which is called Lee. Yeah. Function builders. Function. Okay, better to just a minute, please. I will save the time. I'll just explain this so it can be better visible. That's why I'm just taking the text over here. Okay, so let's say we have an nth order system. We have a nth order system, and this nth order system needs to be obtain Si minus A inverse. Si minus A inverse. That is the Rm. So the conventional way is that adjoint Si minus A upon determinant of Si minus A. That we will not go for. What is the alternative way? Alternative way is that Si minus A inverse, we know the system matrix A with us. Now the system matrix, if it is known, then we can write this Si minus A inverse in this way. And I told that Si minus A inverse is resolved matrix. So this way we can write this Si minus A inverse. Now, how to get these different coefficients which are being used here? Qn minus 1, Qn minus 2, Q1, Q naught, An minus 1. How to obtain this? For this, there are for getting these coefficients and these matrices, Q matrices and A coefficients, there are certain steps. So, step one is that we have already assumed, let's say, order of system is n, then Qn minus 1, that is In. In is the matrix. इसको बोलो चला गया ना सर का लेक्चर है इसको यहाँ नहीं रुके हो. So In is the identity matrix, unit matrix, है ना, of nth order. Just Qn minus 1 we assume to be equal to In, first one. Now An minus 1 coefficient, please remember there is no An coefficients here. An minus 1 coefficient is minus trace Qn minus 1A. So this is just first we need to get the matrix Qn minus 1 into A. So in this case, because this is the identity matrix itself, so this is basically A is the system matrix. So we need to get the trace of that. And what is the trace? If we are given some matrices, trace is just the sum of diagonal elements. That is the trace. So minus of this. So step 1 is completed. Ready? Step 2 is Qn minus 2. So what is Qn minus 2? Qn minus 1 A plus An minus 1 In. So because we have already obtained Qn minus 1 in previous step, we have already obtained An minus 1 coefficient in previous step. So we can get easily now Qn minus 2. Now once we get Qn minus 2, we go for An minus 2 coefficients. An minus 2 coefficients, which is nothing but minus 1 by 2 trace of Qn minus 2 into A. Now A is already known, which is the basic things which we know. With Qn minus 2 we have just obtained. We will multiply this and into 1 minus 2 and minus. That will give me second coefficient. This way I will keep on going. And finally, what I get? I can get the intermediate coefficients as well, right? And in last, let's say I go to last step, nth step. So in nth step, Q naught is Q1 A plus A1 IN. And so Q1 obviously we must have obtained in the previous n minus 1 step, A1 also in previous n minus 1 step. Now finally A naught is equal to minus 1 upon n trace Q naught A. So in this way we got all the coefficient, all the matrices. But now one may say that okay, we got these different matrices and coefficients which we put here directly, and we can get the transfer function. But what is the guarantee that these coefficients and these matrices which were obtained, they are correct only? How to check? So the good thing is that in this algorithm, this is the check. After obtaining everything, if you find Q node A plus A node into In, you simplify this and it comes to be a zero matrix or zero vector, right? Basically zero vector. Then no, this will be zero matrix. Nth order zero matrix. This is a nth order zero matrix. If this is the nth order zero matrix, then we can ensure that whatever steps we have carried out, whatever coefficients we have obtained, whatever matrices we have calculated, they are correct only. So this is the check. So now this was for nth order. Now let's say if we have only second order, then how many steps will be there for second order? Only. Okay, so for second order, there will be two steps only. Okay, n equal to 2 if second order is there. So step 1, you put n equal to 2 here. What will be the q1? Q1 will be I2, right? Which is nothing but 1 0 0 1. Now what will be the A1? A1 will be nothing but minus this, and Qn minus 1 is this matrix itself multiplied by A. So this will be nothing but minus trace of A. So that is our step 1. Step 1. Now what is step 2? Step 2 is you just put n equal to 2. So you come to Q naught, right? Q1 A plus A1 I2, that is Q naught. So Q1 we know already, A we know already, A1 we know, I2 we know. So this will be Q naught. Now what will be the A naught? You put n equal to 2 here, so you'll get minus 1 upon 2 trace of Q naught into A. So you have got A naught also, and that is the last step, Q naught, and A naught is the last step. If you got it, then we can easily verify this Q naught A plus A naught IN. If you verify and you find this to be 0, then we can say this is correct only. So this is for second order, it's easy to get anyway by both the way, but for higher orders, I personally have used my PhD for these things, and this algorithm is very much helpful when you go for fourth order and so on. Okay. Now, next is we will implement whatever we have discussed so far. We will try to obtain the model of a DC to DC converter, DC to DC converter, and how these equations helps us, that we will try to find. So let's say this is a buck converter. This is when buck converter is on. We have already discussed this in detail. Okay, so this is the buck converter. Now in buck converter, what we do, we identify that how many steps are there. So obviously there are two. What is that? This is working. Hang हो गया क्या? देखिए. नहीं, ठीक है, चल रहा है. हाँ? Hang हो गया क्या कुछ? Is working? ठीक है. Okay, so this is the switch. This is the equivalent model when switch is off. Now, when switch is on, then we try to write some equations. So yes. So we identify how many states are there. So states are two only because it is a second order model. So here our x will be x of t, you can say x of t, that will be IL of t and VC of t. That will be our state vector, right? Now my pen is not working properly, so you may face some difficulty while writing. So we just get equations from here. This VL equal to VL, which is nothing but DIL by dt, right? DIL by dt equal to, in this case, V input minus VC, right? Second equation we will get for this current. So that is IC C dVC by dt equal to IL minus I node. I node is nothing but V node upon R, and V node is equal to VC in this particular case. So we can write directly minus VC upon R, right? That is the second equation. Third equation will write for output voltage. So output voltage is, in this case, output voltage is equal to VC. Now we will simplify these equations and try to write in the given standard form. So if I write here, this is DIL by dt, which is equal to minus VC upon L plus V in upon L, right? Similarly, this D VC by dt, that is equal to IL upon C minus VC upon RC, right? And V output equal to, you can write 0 into IL plus 1 into VC, right? So if I write it in state space form, this side, then what do I get? I just better to copy it. I get this equation, right? I form into a DIL upon dt is equal to IL. There is no coefficient of IL, so this will be 0. Then BC is here, so minus 1 upon L will be here, plus V input, that is Vg or V input are same. V input upon L, so that is 1 upon L. Second equation, dVc upon dt. So IL coefficient is 1 by C, Vc coefficient is minus 1 upon Rc, and input voltage is not there, so this will be 0. So this is the coefficients. This is a steady space model representation when switch is on. In the same way, I can represent this equation, output equation. Like this. When switch is V naught equal to, there is no coefficient of IL, 0. There is coefficient of Vc is 1, Vc. There is no coefficient of input voltage, so B 0. So this is, I have obtained the models. Now what I'm getting from here? I'm getting basically with this. This is my A1. This is my B1. This is C1 and this is E1. So this is just for switches on. Now I can do same analysis when switch is off. So when switch is off, I just again write VL equal to L di by dt, which is now nothing but okay, sorry, I have to type in same circuit in both the cases. No, yes, that is wrong. Just wait. Okay, so this is the circuit when switch is off. Now when switch is off, that time I am writing equation for VL. So this VL is equal to L di by dt, which is now minus Vc. Okay, and when I go for IC, then IC is equal to C dVc by dt, which is IL minus Vc upon R, same as in previous case, and V output is same as Vc. So now what I can do, I can easily reformat this in terms of this IL upon dt equal to minus Vc upon L. Now there will be no part of V input. Okay. Similarly, dVc by dt, that will be IL upon C minus Vc upon Rc, and V naught will be just Vc itself. If I write this in matrix form, then I'll get just these equations. Okay, let me write here. These equations. Okay. So if I write these equations in this state space model form, then I will get these equations. So from here, what we are seeing that this dIL by dt, this one equal to minus Vc upon L. There is no coefficient of IL, so it is 0. And similar thing, but here now coefficient of Vn is also 0. So this portion comes to be 0. Now the remaining part remains same. Okay. Similarly, this V naught is equal to 0, 1, ILC, VCT, same because these equations are same. So the lower part remains the same. Now from here, what I got A2, I got B2, I got C2, and I got E2. So these things I needed as A1, A2, B1, B2, C1, C2. Now once I got these things, then what I can do, I get the this is when switch is on. This is when This is when switch is off. So the step 2. So our step 1 is over, right? So step 2 is that averaging the state space equations using duty cycle D over one switching cycle, right? So in that case, what we do, we take both the models and average them. If you obtain this average matrix, then how does the system looks like? It will look like this. Or you can just writing directly A, B, C, and B. So E. Okay. So if you see here, this was our A1. This was our A1. This was our A2. So the A is A1D plus A2 1 minus D, and because both matrices are same in this case, so it will be D plus 1 minus D is 1. So the A will also be the same matrix, either A1 or A2, right? If B I talk, then I multiply this with A1D plus A2 1 minus, both are 0 here, so this will be D upon L. Similarly, both matrices are same, so same matrix will come here. The reason is that C1D plus C2 1 minus D. C2 1 minus D. Okay, so because C1 and C2 are same, so it can be taken common. So D plus 1 minus D is 1, so it is C1 only, right? So it is same. Now E is also there. Now we have obtained this average matrix. Now next step is perturbation will take. Now after the perturbation, what we will do? If we know A, B, C, D, the next step is to get steady state model. To get the steady state model. So next step is, let's see. I earlier preferred that I will write these things, but I think it is taking time is less, so I just pasting it from my slides only. So it's proper visual also. Okay, so steady state model. So steady state model, you know that we have already derived it. So this will be the steady state model. L and C are not visible by switch. They are right to the switch. अभी कौन सा स्लाइड चल रहा है? ये चल रहा है क्या? Steady state state 2 ना? I'll take your doubt later. I could not understand what you have said. We'll take it later. So now what we are doing here, we are just trying to find the average model. So we can directly use the equation. You know, we have one equation we derived previously. X is equal to minus A inverse BU, right? We have A with us now, so we can get easily. So what is X in our case? IL BC, right? And A is this one, so minus A 0 minus 1 upon L 1 by C minus 1 upon RC. What is B? You get this equation B VG upon L into V Vg. Okay, which is nothing but what is this D into Vg? This is no, this is R. This is R. V naught by R. This is nothing but V naught by R, and this is D into Vg's output voltage, which is equal to Vc. Similarly, if you find the V output also, then you can use this formula directly. Y equal to minus C inverse B plus EU will get Y naught also. So this Y, which is V naught, which you will get DC in this case. So that is the way we can get this DC model. Now, how to get the small signal model? That is the important part. So for small signal model or AC model, actually this page is not working properly. Small signal model. So how to get this small signal model? Now we have with us A, B, C, E. We need to find BD. We need to find BD. And this BD, we obtain BD equation. We know that BD is equal to A1 minus A2 into X plus B1 minus B2 into U, right? But A1 and A2 both are same. It will be 0 only, right? A1 and A2 both are same. In previous slide, we have seen that A1 and A2 both are same. So A1 minus A2 will be 0. 0 into X will be 0 plus B1 minus B2. So B1 is 1 upon L, 0. B2 is 0. So difference will be 1 upon L and 0. So this will be 0 into X plus 1 upon L, 0. And U is Vg, right? So if you write it, it is VGL upon. This is your BD. This is your BD. What about ED? ED is C1 minus C2 X plus E1 minus E2 U, right? But in this slide, we have seen that C1 and C2 both are same. C1 and C2 both are same. The C1 and C2 both are same. Similarly, this E1 and E2 both are same. So the difference will be 0 only. The difference will be 0. So this is 0 into X plus 0 into U. So the final outcome will be 0. It means this will be 0. ED will be 0. So we have found BD, ED also. Now it is in our hand that which transfer function we want to find. Next is SI minus A inverse. SI minus A inverse. SI minus A inverse, because this is required in all the transfer functions. As first we find, let's say SI. First we find SI. So S into I, which is unit matrix. So this is S 0 0 S minus A, and A is already known to us. A is known to us. What is the A? A is this one, 0 minus 1 upon L, 1 upon C, and 1 upon RC. So let us put it here. So 0 minus 1 upon L, 1 upon C, minus 1 upon RC, right? So this comes out to be as 1 upon L minus 1 upon C S plus 1 upon RC. Now we need to find the inverse of this. We need to find the inverse of this. Because this is second order, simple second order equation, we can directly find Si minus A inverse. So 1 upon denominator, it's a determinant. So that is the S square plus 1 upon RC into S and plus 1 upon LC. So that is its denominator. And what about this? We need to find its cofactors. Then need to take transpose. So finally, it comes out to be S plus 1 upon RC. Here it will be S. Here it will be minus 1 upon L. But when we take transpose, then it goes up here. And this will be 1 upon C. So this is Si minus A inverse. This is Si minus A inverse. Now, but if I'm using Leverrier algorithm in this case, then I need not to calculate this Si minus A. What will be my Si minus A inverse? In that case, if I go to Leverrier algorithm, so then let's say first I will define this Si minus A inverse. So in that case, Si minus A inverse will be Q1S plus Q naught upon S square plus A1S plus A naught, right? So this is the final thing should come. Now what is the step one? What is the step one? Step one is we define Q1, which is nothing but I2, right? Then A1 will be what? Minus trace of Q1 into A. And because Q1 is identity matrix, so it will be same as A only. So A is with us, A is this one. So what is the trace of this? Minus 1 upon RC, and 1 minus is there. So this will be 1 upon RC. Step 2. What will be step 2? Q node. Q node is equal to, put n equal to 2 over there. So this is Q1 A plus A1 I2. This is our Q node. So Q1 into A. Q1 is nothing but I2 only. So it will be same as A only plus A1 into I2. A1 is here. So I2 is 1 upon RC, 0, 0, 1 upon RC. So if I add this A in this A1, what I will get? This is 1 upon RC. Right? I'm adding here. I'm adding here. So this is minus 1 upon L. This is 1 upon C. 1 upon L. Actually, my pen is not working, so you will face some difficulty for this session. Next session will work problem. So minus 1 upon L, and this is 0. This is Q node we got. Okay, Q node we got. Now, what is the A node? A node is minus half. Then trace of Q1 into A. Q1 into A. So if you simplify it, you will get this comes out to be 1 by LC, right? 1 by LC. So like that, we got A1 A node and Q1 Q node. Similarly, we can get we can check that this Q node into A plus A node I2. This comes out to be 0. This comes out to be 0, that we can check. Now, if we put it back, this Q1, Q2, so you will get this 1 upon S square. What is the A1? A1 is 1 upon RC into S. What is the A2? A node, that is 1 upon LC, right? What is Q1? S. So Q1 is nothing but this is the matrix only. So plus Q node, and Q node is this one. So you get S here S plus this matrix. So this is plus 1 upon RC, right? Minus 1 upon L, 1 upon C. So what you see here, that this matrix and this matrix are same. But for second order, that ideal buck converter, it's quite easy both way. But if this is the higher order, then this second method works well. Okay, so we got Si minus A inverse also. Now everything we have got. Now only thing is that whatever transfer function we want to opt, that we can directly obtain using the formulas. So let's say we want one transfer function which is x of s with respect to d of s. For that formula was Si minus A inverse, Si minus A inverse into BD. Now we have Si minus A inverse. Actually, I'm not able to write it properly. Sorry, let me try. Si minus A inverse. So just now we have written Si minus A inverse. S square 1 upon RC into S plus 1 upon LC. And what was the inside equation? This one, S plus 1 upon RC. So I'm just writing this S plus 1 upon RC plus 1 upon RC minus 1 upon L 1 upon CS. So this is Si minus A inverse into BD. And what was our BD? If you remember, this is BG upon L and this is 0. Right? So this was our BD. BD, VG upon L, 0. So we can simplify it now. So if we simplify it, then what we get, basically we need to multiply this. So first one is 1 upon S square plus 1 upon RC S plus 1 upon LC, and you multiply this with L. So this is VG upon L S plus 1 upon RC. Okay? And this will be 0. Now the upper this plus 0. Now lower is VG upon LC plus 0. So here we are having two transfer functions because this is the vector in which we have two rows, one column only, and this denominator will be with all. So what we can see here, this is VG upon L S plus 1 upon RC, S plus 1 upon RC divided by S square plus 1 upon RCS plus 1 upon LC. Similarly, here it will be VG upon LC divided by S square plus 1 upon RC into S plus 1 upon LC. We got two transfer function. And what is these two transfer functions basically? Here we have denominator is d of s, right? So it means we got two transfer function. One is IL of s upon d, which is the this one. Second is VC upon d, which is this one. So this way we got here these two transfer functions with respect to duty cycle. If I'm to take, I need to take variation in inductance with respect to input voltage input, then I have to take here U of S, which is VG in this case, and then this BD matrix will change with B. So corresponding to B, whatever is there, that will come. That is 1 upon L, and this is 0, and correspondingly, this VG will disappear from both. That will be your with respect to BD, with respect to input voltage. Now, second is we want to find, let's say, the V node upon D. V node upon D. If this is the case, then what formula we will use directly? This is the formula which we can use. This one. C Si minus A inverse BD plus ED. Okay. C Si minus A inverse BD plus BD. Okay, so we have C with us, that is 0, 1. SI minus A inverse will be the same, right? And BD will be the same. So if you put this SI minus inverse BD over here, then we will get again the same things, whatever we got here. Okay, if you simplify, then we will get this only here plus ED. And what is the ED? We just calculated. That is ED. Where did we calculate? Yeah, here itself. ED is 0. So let us put it back here. ED is 0. What we need to do? We need to multiply this with 0, 1. So if I multiply this with 0, 1, so first term will be 0, only second term will appear, and this is already 0. So this will be Vg upon LC upon whatever this denominator is there, right? So V0 upon T, same age. Obviously, I am not put here. This is of us. This is same age Vc upon D. Why it is coming? Because we have taken the ideal capacitor. That's why the voltage across capacitor and voltage across load both are same. But if we have considered the ESR, then what could have happened? The effect of RC would be there. Then VC, then these two transfer function will definitely be different. In that case, these two transfer function will definitely be different. So this way we see that we can get the transfer function of any system. We just need to know their individual matrices. After that, we need to get A1, A2, B1, B2, C1, C2, and E1, E2. Once they are obtained, then we can easily find out any transfer function depending upon our control requirements. Okay, so with that, I think you got some idea about this state space averaging technique. Now there is one more technique which I will tell in the afternoon lecture. If any doubt is there, please ask. We have some time with us. I'm sorry, in last some half an hour it got disturbed, so I could not write well. If you have any doubt, please feel free to ask. If any of you have any doubt related to this modeling of converters, L and C are in this circuit. Advanced topology which has many mode of operations. Yes. How to average them? In same way, right? Like I said, if let's say your converter is operating in 4 modes, so mode 1 will operate, let's say, for some time, D1 into T. Mode 2 will operate sometime D2 into T, let's say D3 into T, D4 into T. So every time in each mode, your circuit will behave linear. Like in buck is this buck converter simply, if I say, whenever switch is on, we have one circuit which is linear. Whenever switch is off, we have one circuit which is linear. True. Now, similarly, when you have multi-switch, more than one switch, two switch, then like if you go for this multi-port converters, then you have 3 modes, sometimes 4 modes, right? Then you keep one switching cycle to be constant. Within that cycle, only those modes are repeating. Even if you go for when we will read this soft switching converters, they go for 4 modes. But whenever one particular mode is happening, then we have linear circuit in which either our voltage is there or your switch is there, and inductor capacitance. Those equations are there. We can easily write their equations. So in that case, we will write those equations. We will get one particular model for that particular mode. Then similarly for next mode, for third mode, for fourth mode, right? So individual mode we have obtained. Now we also not know that for how much time each mode is operating. Let's say first one is for T1 period, second is T2 period, third is T3 period, four is T4 period. Sum of all those are capital T, right? So what you will do now, T1, T2, T3, T4, these 4 times of 4 different modes, they must be function of some duty cycle. Definitely, maybe if there are 2 switches, 2 duty cycles will be there, 3 switches, 3 duty cycles will be there, right? Now, once you got this, then you will multiply each mode equations with these time intervals, then divide by T. So now capital T will cancel out. Only thing remains either your state variables or system parameters or these duty cycles only, right? And same approach we do. If someone is asking, let's say there are 2 duty cycles, then you will have BD1 and BD2. This will change. Some equations will come in terms of D1 plus some equations in terms of D2, right? So you will get this U term as BD1, this term U term as BD2. Now you can find X with respect to D1, X with respect to D2, right? So if there are D1, D2, what they are? They are just basically control variables, right? So you have 2 control variables. Now in multi-port converter, we do same. But what happens sometimes that these cross coupling and all those phenomena, cross regulation and cross coupling, those issues occurs in multi-port converters. Then we use decoupling and all. That is the different control approaches, right? But yes, variation of this duty cycle D1 may occur on both the output voltage if there are multiple output. So that we need to know by this way only. Then these generalized step, those remain same. Only the number of these control variables, number of duty cycles based upon switches, they keep on increasing. Accordingly, this BD1, BD2, they keep on increasing. Okay, so I hope that answers the second question also. Someone has put in chat. Sir, for multi input systems, inverse matrices, how can we solve? Madam, same way. Multi-input is there, it means your VG will be VG1, VG2, VG3 like that. So your B matrix will change. Now B matrix, capital B matrix, that will have more rows. Right now, okay, right now what is happening? This is B only because we have only one input. These rows are representing number of state variables and these columns are representing number of inputs. Now you have only one input VG1. If multiple inputs are there, then these rows will be like this. So this is for first input, this is for second input. Okay, so right now there are 2 transfer functions only. In those cases, there will be if 2 inputs are there, 4 transfer functions. Now these 2 variables will also be there. So I hope I answered your question somewhat. Any other query? Any other query, please? Okay, if not, then we will close today's talk over here. And just I say afternoon, we will take another averaging modeling, which gives the same average model, but same model, transfer function model, but the approach is different, right? The approach is different. So that we will do in afternoon. And now in evening, we will also have a quiz. So please be there. If you can complete, so they will inform you. The nature of quiz is such that if you are well connected, it will start, and whatever time is given, you have to complete in that time only. But it is flexible that maybe if you are not, in that time you are not comfortable to submit, then maybe after some time also you can try. But once you start, then you have to complete it in the given time frame. So instructions will be given to you. Better to complete it in the 3:30 to you have asked one question about chat. Yeah. For single switch only, D on and D off with 3 modes of operation. In D on and 3 modes of operation and D off. Okay, that's what I said. Let's say DCM mode, I said. In DCM mode, what happens? When switch is on, current is increasing, then one mode is there. When switch is off, now there is 2 modes. One is when inductor is carrying the current, inductor current will reach to 0. Then after some time, inductor current becomes 0. So the part of the D off, that will constitute different circuits, right? So similarly in your case also, let's say when D on is there, switch is on, then there may be 3 modes. Because 3 modes are there, I think these are there due to some diodes or maybe some other components is on or off. But if let's say switch is on and the current through the different components, maybe inductor, capacitors, they are continuously increasing or decreasing, right? Then there will not be different modes. We cannot say to be different modes. But if in some diode gets on or something happens and in some component 0 modes, and for those different modes, you will be in different time, right? For example, again I say 100 microsecond is total, let's say, and D on is 50%, 50 microsecond, D off is 50 microsecond. Now you are saying within this 50 microseconds, you have some 3 modes. One is for 10 microsecond, another let's say for 50 microsecond, third one is let's say for 25 microsecond. So if you are having 3 modes, then you must have 3 circuits for that purpose, right? If 3 circuits are there, then first circuit you will write state space model, multiply it with 10 microsecond, plus second circuit, multiply it with another 15 microsecond, then third one another 25 microsecond. Like that we can do averaging. But if we are saying mode are different but circuit remains the same, then I think we cannot say different modes. Then a number of modes will be reduced only. Is it okay what I'm saying, Nitish? Okay, so it's a basic mathematics only in state space averaging, that whatever number of state space model, you just multiply the time for which they are, they are functioning, then take average. So it's doable. Okay, then we stop here and we'll meet in afternoon again. Sir, for multi-input systems inverse matrix, how can it be solved? Okay. So, madam, inverse matrix, the procedure remains same. The only thing is that how to obtain the A, right? So, obtaining A will depend upon the number of energy storage elements. Size of A depends upon the order of the system. So, if you are able to write the basic equations for each mode, average it, you'll get the A. And A is called system matrix, and that is only required for inverse. Other matrices are just no inverse is required. They are just addition only or subtraction. Okay, then we now taken off for you are getting that is okay. 5 by 5 na, so you use better this Leverrier algorithm which I have just told you, because going through conventional adjoint divided by determinant, that you will make mistakes in that. But if you use this Leverrier algorithm, then step by step you can do it. And even you can write the code of this Leverrier algorithm in the MATLAB, and you can get your coefficients and matrices very easily. So you can get direct transfer function also. Okay, yeah, is there? Yeah, this one. Man. So if it is fifth order, you put just n equal to 5. You need to follow 5 steps, and you will get it. Can we get neglect? Can we get neglect them to reduce complexity? The modes with small time, does it make any effect? Yes, it may make effect if you are saying neglect them to reduce complexity. Okay, so if the you can neglect only if the whatever action is taking place that affects the operating point very slightly, but if has long impact or large impact on the operating point, DC operating point, then we cannot. The dynamics of the converter, which is there for shortest period of time, or whatever short period of time you are saying, if that dynamics affects a lot to the steady state value or DC operating point, then we should not neglect. But if that dynamics is very close, let's say with some slope in one mode, inductor current is varying with some slope. In another mode, is some 10% difference, or maybe 5 or 10 difference, then it will not make a difference. But if suddenly the current reduces with another slope, then it makes a difference. So in that case, we have to check. It will, it will depend case to case. So better if it is not there, we can merge it that dynamics with another mode if it is for short period. Sir, including parasitics or without including it in these equations will give appropriate result. Yes, actually, if time permits, I will show you the some slides in afternoon session first, where these parasitics I have included in this buck converter, and what is the difference between the results, that I will show you in afternoon. Okay, so I'll show you that what is the difference when we use the parasitics and when we do not use in transfer functions. Also, we have to see the state variable behavior in that mode. We have, yes. If it is impacting, then we cannot. Because the reason is that when we are designing a controller, we assume that whatever model is there, we have obtained, that model is the actual system. And this model is now obtained based upon the linear approximations, or based upon these perturbations around the DC operating point. Now, if the DC operating point itself varies a lot due to some reason, then this controller may not work properly. That's the reason. So as accurate as this model is to the real system, by neglecting some dynamics, even definitely when we do mathematical modeling for even mechanical systems, we do not take the things like everything in everything into consideration. Still we get good results, because those things may not let's say time constant, if some system is having very fast and some is very slow. So what we do, we normally neglect the fast one and we take care of the slow one, and we accordingly design the controller. Though this fast one is there, but we neglect. Why? because we think that if we are designing controller for the fast one, for the slow one, then this will take care. Like if you are having, let's say, very less space in pocket, and you are given, you can put only 10 notes in your pocket, and someone is giving you some 10 rupees 10 notes, and let's say 500 rupees 10 notes, then what will you do? It, you will take only 10 500 rupees note. It does not mean ki these 10 notes of 10 rupees does not have any value. They also have value, but because you have limitations, so what you are thinking that, okay, I have already 5 into 10 5,000 rupees. If I need to get something with worth 10 rupees, then I can use this 500 rupees will work. But reverse is not possible. If you take care of 10 rupees notes, you put it, and if you need something worth 500 rupees, then you cannot purchase with 10 rupees notes. So if we take all those things into consideration, then that is the best one. But considering the limitation and cost associated with different components, we neglect the less important things. Okay, thank you. Okay, so we'll meet after lunch, 2 o'clock. Thank you.